Good morning. In section 6, we're finally going to do some full hypothesis tests. Hi guys, I realized while editing this video that I referred to it as being section 9.6, but it is definitely section 9.5. So the video is named correctly, the video is listed correctly in Classroom, but in the video I referred to it as 9.6. Hopefully that doesn't bother any of you too much. Up until this point, we've been learning how to identify the null and the alternative hypothesis, how to identify type 1 and type 2 errors, figuring out what distributions we're going to use, under what circumstances, and all that leading up to this section. So before we do our first hypothesis test, some additional pieces of info I just want to run past you. First, always make sure that you know what the significance level is before you start your hypothesis test. Okay, it's real annoying to get down to the very last step and then realize that you don't know what you're supposed to compare your p-value to. So get all that figured out in advance. And just know that if alpha is not given to you, then the most common standard value for alpha is 0.05. Okay, so there are some names given to tests that you might want to be aware of, or that you probably should be aware of, and they have to do with the bell curve. Okay, if you picture in your mind what the bell curve looks like, we know that it has the big peak in the middle, and then it has two tails on either side. So we refer to different kinds of tests based on the tail that we're talking about. So if your alternative hypothesis is a less than type of hypothesis, then we call that a left-tailed test, okay? Because that p-value would be describing an area way out in the left tail of the normal bell curve. On the other hand, if the alternative has a greater than symbol, then that would be a right-tailed test. And if, on the other hand, your alternative hypothesis has a not equal to symbol, then we call that a two-tailed test. All right, so those are important. The names are kind of important because you may hear them at some point in the future in a different setting, and you want to know what they mean. But we definitely want to be paying attention to whether the alternative hypothesis has less thans, greater thans, or not equal tos, because that's something we're going to have to plug into the calculator. Okay, so we want to have an idea of what kind of tail our test has, even if we're not going to necessarily name it by that. So remember, thinking about the p-value, just for a moment, assume that our significance level is 0.05. If we have if we have a p-value that is much smaller than alpha, then we're going to have more confidence that our answer is correct, right? So suppose, for example, you have a p-value of 0.01, comparing that to 0.05, well, 0.01 is quite a bit lower. But on the other hand, if you had a p-value of 0.046, that's just barely underneath that alpha value. It's just barely lower. So when you state your conclusions, you may want to refer to whether or not the p-value was kind of close to the significance level, or if it was, kind of a blowout. There was no question that the p-value was lower than alpha. Okay. On the other hand, if our decision is to not reject the null, to fail to reject or decline to reject, then it makes a difference whether the p-value is 0.052, right, just barely higher than that alpha, or if it's 0.4, which is 80 times what we needed to be in order to fail to reject. So it's a not 88. I'm being silly. 8 times greater. So again, the closer we are to the alpha value, maybe the less confident we are. If our p-value is significantly different from alpha, then that's going to mean something to us, and we may want to refer to that in our conclusions. Okay, so whenever possible, try to apply your own reasoning. Make sure that if you're going to make a strong conclusion about something, that it actually has practical significance. Okay, don't just assume because the p-value is less than alpha that the null hypothesis is absolutely blown out of the water. it may not necessarily be the case. Okay, so try to use common sense. All right, so for example number 1, we're going to do some of this on the document camera with our calculator, but before we do, we have a lot of things to point out. So it says Jeffrey is an 8-year-old, established a mean time of 16.43 seconds for swimming the 25-yard freestyle, with which he had a standard deviation of 0.8 seconds. Okay, so his dad gives him some new goggles, and he times him 15 times in this 25-yard freestyle, and his mean for that 15 runs was 16 seconds. And so Frank thought, that the goggles helped. So we want to conduct a hypothesis test to see that if that 16-second average for the 15 swims is actually statistically significant. Okay, so we're going to use an alpha value of 0.05, and we'll assume that the distribution is normal. So this is a test of a mean, right? We're talking about the mean time for this young man's swimming. We are given the population standard deviation, so we know that with that standard deviation we can use the normal distribution. Okay, we have sigma. Remember, population standard deviation is sigma. So we're going to use the normal distribution with a z-test. All right, the function we'll use in the calculator is z-test. I'll show you that when we get to the document camera. All right, we want to identify the null and the alternative hypothesis. So remember, I've tried to teach you guys to write out what the claim is and what the opposite of the claim is. So in this case, the claim is that the mean is less than 16.43, and that claim becomes the alternative hypothesis. And then the null hypothesis would be that mu, you could do this two ways. Mu is greater than or equal to 16.43. That's the way I taught you to do it. I noticed, however, that your textbook varies from what I taught you a little bit. So, so your textbook would probably show this as being mu equals 16.43. So I think from here on out, I will accept either equals or greater than or equal to. And then we're going to use an alpha of 0.05. So that should be all the information that we need in order to go over to the calculator and figure out what our p-value is so we can make a conclusion. So from here on out, we'll switch over to the document camera to do that. Okay, for example 1, I've written down all of the pertinent information from our example. We have our null and alternative hypothesis. It's always important to keep those in mind. We have our x bar from the samples, our sigma that was given, and our n, which is, remember, the sample size. So I should also probably write down alpha is 0.05. So with that information, we can go to the calculator and start our z-test. So I've zoomed in a little bit more than I have on previous examples, hoping that you guys will be able to see this clearly and follow along. So what we're looking for is z-test. So if we go to the stat menu and then we go over to tests, it's the very first thing in the list. So z-test. We have the choice of data and stats, and we're going to choose stats because we have the statistics from these 15 samples. We don't have the raw data itself. In mu naught, mu 0, okay, that's where we put the number that is in our null and alternative hypotheses. So in this case, that's 16.43. In our sigma, we put the standard deviation that's given, which is in this case 0.8. Our x bar is the mean from the samples, which is 16. And then we have n, which is the sample size, which in this case was 15. It was right, 15 25-yard swims. So the last line we want to match to our alternative hypothesis. Notice our choices are not equals, less than, or greater than. And you just want to match the symbol as it's written in your alternative hypothesis. So we see mu is less than 16.43, so I have highlighted less than there, and then we hit calculate. So the most important piece of information in here is p. Okay, we see that we have a p-value of
0.0187. Okay, I'm just going to round that off at the fourth decimal, kind of arbitrarily. No real reason to go to 4 decimals, just I had to stop somewhere. So based on this, we compare our p-value to our alpha. All right, I'm going to move the calculator off to the side for now. And we see that the p-value is definitely less than alpha, right? 0.01 is quite a bit less than 0.05. So because the p-value is low, we reject the null hypothesis. Okay, that's H naught. So p-value is less than alpha, we reject. So now, remember that the original claim is that his mean is less than 16.43. So if we reject the null, that means that the data is supporting this alternative hypothesis. And the alternative hypothesis is the claim in this case. So the way we would want to write our conclusion is that the data supports the claim that, let's see, what was his name? Jeffrey, yes. Supports the claim that Jeffrey swims faster with the new goggles. All right, so please understand that the conclusion at the end is probably the most important part of this whole process, okay? It makes no difference to me whether or not you can calculate a p-value if you don't know what the p-value means and you don't know how to make a final conclusion from it, okay? So there's example number 1, and I think we're ready to move on.
For example 2, we have some data here for test scores. Okay, we have a group of students that believe that the mean is 65 for some test scores, and the statistics teacher thinks that the mean is higher than 65. So he samples 10 stat students and gets these scores. Okay, it looks like it ranges from 65 to 72. Performs a hypothesis test using a 5% level of significance, so that's an alpha value there, 0.05, and we are assuming that the data is from a normal distribution. So once again, we are testing a mean. However, this time, notice that we are not given a standard deviation at all. Okay, so consequently, if we're going to do a test of a mean, but we don't have the population standard deviation, then we're going to have to use the t-test in our calculator. Okay, this is not going to be the normal with the z. It's going to be a student t-test with a t. All right, identifying the mean again, the null and alternative. The null would be that the mean equals 65, and the alternative would be that the mean is greater than 65. We would, get that from writing out the claim and the opposite, and then assigning the alternative based on that. And then we have an alpha of 0.05. Once again, we'll go over to the document camera to find the information that we need on this.
For example number 2, we're going to test a mean again, only this time we're not given a standard deviation, so we're going to change to using t-test. Another difference in this example is that we are not given the sample mean and the sample standard deviation and all that stuff. We are just given the data. So with this information here that I've written down, the null and alternative hypothesis, the alpha, and then the data, we can go to our calculator and we can put that data into L1. So remember, to do that, you hit the stat button, you hit enter on edit. I've already put these numbers in here for the sake of time. So if you want to pause the video and type those numbers, go ahead and do so now. Once you have those in, second quit, you go back to the main screen here. We hit stat, we go over to tests, and this time we're looking for t-test. All right, so t-test, this time we're going to tell it data instead of stats because we don't have the stats, we have the raw data. So we select data, our mu naught is 65, the list that it's in is L1, frequency should just say 1, and then we want to match this to the alternative hypothesis again, which is greater than, so we want to say greater than the third option there, and then we calculate. So, once again, the most important thing in this screen is the p. So we get a p-value 0.0213. So comparing that to alpha, we see it once again that the p-value is less than alpha. And so once again, we will reject the null hypothesis. All right, so in this case, the students believe that the mean is 65. The instructor believes that the mean is greater than 65. So what we might want to do in our conclusion is say that the data supports the instructor let's say the instructor's claim that the mean is greater than 65. Okay. So again, most important thing about all of this, as far as I'm concerned, is writing that conclusion correctly. We want to say it in such a way that it's true, right? So the data supports the instructor's claim. We didn't prove his claim. We have to be careful not to say too much, but definitely based on this data with a p-value of 0.02, the data supports the instructor's opinion or his guess that the mean was greater than 65.
For example number 3, this is our first shot at testing a proportion. We have someone who believes that 50% of first-time brides are younger than their grooms. So we're going to run a one prop z-test this time, okay? Anytime you have a proportion, you're going to do one prop z-test. There's no real decision to make about z-test or t-test. If you determine that what you're dealing with is a proportion, it's automatically one prop z-test. So we have 100 first-time brides, 53 said that they're younger than their grooms, and we're going to use a 1% level of significance, so alpha is 0.01, and we see our null and alternative hypotheses there. So we'll turn over to the document camera to finish this one up as well.
Example 3 gives us the first chance to test a proportion. With proportions, once you've identified that you're dealing with a proportion and you've established what the null and alternative hypotheses are, then the nice thing is there's no decision to make about what distribution you're using. It's got to be one prop z-test. That's the only one we can ever use with proportions. So to find that, we go to stat, we go over to tests, and we're looking for one prop z-test, which is number 5 on my TI-84 Plus. So we hit enter on that. P0 is the number in the claim, or in the null and alternative hypotheses. So that's 0.5. I've written these in a different order than they asked for in the calculator. Our N is our sample size, right? She says that she sampled 100 first-time brides. 53 said that they were younger. So X is 53. Okay, that's the number of successes, the number of successful responses. So N is the sample size. That's 100. And then we want to match this to our alternative hypothesis, which is a not equal to in this case. So that's the first option. So now we're going to calculate, and we see that we have a p-value of 0.5485. All right, so in this case, this time we see that the p-value is actually significantly greater than alpha. Okay, in our first two examples, the p-values, I think, were pretty convincing that we should reject the null. But on this one, it's an absolute slam dunk that we would not reject or fail to reject, however you like to say it, the null hypothesis. Okay, fail to reject or decline to reject, whichever, like I said, however you like to say it. So what does that mean about our claim? Okay, well, the claim this time actually was the null hypothesis. Okay, if you read that first sentence in the example again, it says June believes that 50% of first-time brides are younger than their grooms. Okay, she's saying that it's 50%, exactly 50%. So, in this case, her claim is the same as the null, and what we have decided is that we cannot reject the null hypothesis, which means we cannot reject her claim, because her claim is the same thing as the null hypothesis. So the way we're going to phrase this conclusion is different from the other ones. Okay, the first couple of examples, the claims lined up with the alternative, but this time the claim lines up with the null, so we need to change the way we say it a little bit. So we're going to say that there is not enough evidence to reject June's claim that 50% of first-time brides are younger. All right, so because June's claim was a claim of equality, we can't say that we support her claim or we don't support her claim. We can only say if there's enough evidence to reject her claim or not enough evidence to reject her claim. In this case, because we failed to reject the null, we'd say there's not enough evidence to reject June's claim. So there's example number 3.
All right, so hopefully these hypothesis tests are now a little more complete to you. Maybe a little more satisfying now that we've done all of it. We're putting it all together, and hopefully it's all making sense. This is something that I think takes a little practice. You know, really coming up with that conclusion, writing that good conclusion, that's probably the most important part, the part that needs the most practice. So hopefully you guys won't have any trouble with that, but if you do, please send me an email, let me know. I'll be happy to help. All right, you guys take it easy. Talk to you later.